Hello everyone, my name is Komasinyolo. Welcome to another video by Attention Matrix, where we try to make learning fun and easy. Please comment, like, and subscribe if you would like us to continue making this content and you enjoy it or find it helpful. Now on to the next video. Let's get right into it. Okay, welcome to another video on momentum. In this video, we will be focusing on elastic momentum and we'll be doing an example. Okay, so this video is essentially to demonstrate the principle of elastic momentum through an example. Okay, and the example is on the screen there. So let us go right on ahead and solve it. Okay, so the example is as follows. It says, two balls with the same mass collide elastically. Okay, so it's an elastic collision. Two balls with the same mass collide elastically as indicated in the diagram. Ball A has an initial velocity of 2 meters per second. Okay, by ball A, I suppose they mean ball 1. Okay, so ball 1 there, this ball here. Okay, that's ball A. That's what they call ball A. We'll call it ball 1. Okay, so ball 1 has an initial velocity of 2 meters per second east, and after the collision it has a velocity of 0.2 meters per second in the same direction, so east still. Okay, calculate the velocity of ball 2 before the collision. Assume that the velocity of ball 2 is in the same direction as ball 1 and ignore the effects of all external forces. Okay, so that's our question there. That's our problem there. So let's go right on ahead and see what we can do. Okay, so momentum elastic collision example. Okay, so we've got the following. We've got a ball, right? And the ball is moving in that direction with a velocity of 2 meters per second. Is it 2 meters per second? 2 meters per second. Yes, it is. And this is ball 1, right? And we've got ball 2 here also moving in that direction. Remember, in the question they said assume, that's the last line there, they say assume that the velocity of ball 2 is in the same direction as ball 1 and ignore the effects of all external forces. Okay, so we are assuming that this ball is ball 2 is traveling east as well. So this is the east direction, is traveling east as well, just like ball 1, but you're asked to calculate its initial velocity of ball 2. Okay, before collision, right? This is what we're asked to calculate, and we are told that after the collision, ball 1 continues to move to the east with a velocity of, okay, so let's say ball A has an initial velocity after it has a 0.2 meters per second. Okay, so now it has a velocity of 0.2 meters per second, okay, to the east. And this is after it collided with ball 2, but we are asked to calculate the initial velocity of ball 2, so we also don't know the final velocity of ball 2. Let's see. We don't know the final, calculate the velocity of ball 2 before the collision. Assume that the velocity of ball 2 is in the same direction. So we don't, okay. So as far as this question goes, this is a closed system. What does it mean that it's how do we know that it's a closed system? Well, if I go back to the picture, if you look at the last line there, it says, assume that the velocity of ball 2 is in the same direction as ball 1 and ignore the effects of all external forces. That's a key line. Ignore the effects of all external forces. What does ignore the effects of all external forces mean? It means that this is a closed system, or it's an isolated system. And what do we know about isolated systems, the law of conservation of momentum applies. Okay, so momentum is conserved. So the momentum in the system is conserved. The momentum that you start off with here is the momentum that you end up with there. Okay, so we're going to use the conservation of momentum principle to help us. Okay, so let's jump on right ahead and solve. We are asked to solve for the initial velocity of ball number 2. And what else are we told? We are told that the masses of the balls are all the same. If I go back to the question, we're told that M1 is equal to M2, which is equal to M. So if you look at the diagram there on the right, just below the diagram, we've got M1 is equal to M2, which is equal to M. So all the masses are M. Okay, so I'm going to call all the masses M. So all masses R, M. That's the masses of all the balls. Okay, so let's analyze this situation a bit further. Now we are asked to calculate the initial velocity of ball 2. But what do you notice here? We've got two unknowns. We've got the final velocity of ball 2 and we've got the initial velocity of ball 2. Now, the law of conservation of momentum only gives us one equation. But if we have two unknowns, we need two equations. So this is the general rule, right? If you have one unknown, you need one equation to solve it. If you have two unknowns, you need two equations to solve it. If you have three unknowns, you need three equations to solve it. If you have four unknowns, you need four equations to solve it, and so on and so forth, right? That's mathematically how it works out. So then we will need a second equation in this case. But how are we going to find a second equation, and where are we going to find a second equation? Before we get to the second equation, let's start off with the first. Okay, so with the first equation, we know that we're going to use the law of conservation of momentum. So we know that P total, right, the total momentum is conserved. So P total initial is equal to P total momentum final. Okay, final. So if the total initial momentum is equal to the total final momentum, then it means that our total momentum in the system is conserved. So we're just going to use the equation for momentum as we've been doing this entire time. So we know that for ball number 1, we've got mass, because we know that the masses of all the balls is equal to m. So it's m times velocity, initial velocity of ball number 1, right? Plus, that's the momentum of ball number 1, plus mass of ball number 2 times the initial velocity of ball number 2. This is what we've been asked to calculate. It's our unknown, right? All of that is equal to the mass times the final velocity of ball number 1, which was given in the question, plus the mass of ball number 2 times the final velocity of ball number 2, which we don't have. So we have two unknowns, this unknown and that unknown. As a matter of fact, our masses are also unknowns, but our masses, doesn't matter that our mass is an unknown, because you can see that every term in this equation has m. Every term has m, so if we divide everything by m, then the m will disappear, right? If we divide everything by m, right? I'm going to put it on the side there. Divide everything by m, then I'm going to divide this by m, I'm going to divide that by m. The reason I'm dividing everything by m is so that I'm only left with two unknowns. I don't want to have three unknowns, because then I'm going to have to find a third equation to solve this thing. So I want to remove this other unknown so that I don't have it. So I divide the entire equation by m, and I can do this because every term has an m in it. So this m and that m will cancel, that m and that m will cancel, this m and that m will cancel, this m and that m will cancel. So what do I have left? What I have left is the following. I've got initial velocity of ball number 1 plus the initial velocity of ball number 2 is equal to the final velocity of ball number 1 plus the final velocity of ball number 2. Okay, so now I've got just my velocities in my equation of momentum. So I've been given some of the velocities. So going back to the question there, we have the initial velocity of ball number 1, and we have the final velocity of ball number 1. Okay, so those we can substitute into the equation. So I've got the initial velocity of ball number 1, that is 2, okay, plus the initial velocity of ball number 2, I don't have it. That I don't have, is equal to the final velocity of ball number 1. They gave it to me, that's 0,2 east, right? So it's still positive. Remember, direction is very important when you're dealing with momentum, because momentum is a vector and velocity is a vector, so you need to specify directions. So all of these are moving east. You can see from the question that all of these are moving east, and what we have there at the bottom is plus the final velocity of ball number 2, which we don't have. Okay, so now we've got a much better looking equation. Okay, we've got a nice looking equation. We are asked to calculate the initial velocity of ball number 2, which we don't have, and we also don't have the final velocity of ball number 2. Okay, so what I'm going to do here is I'm going to make the final velocity the subject of the formula so that I can solve my initial velocity. Okay, so I will say VF2, I'm going to make this the subject of the formula. Why am I choosing to make this the subject of the formula? Because remember, we have to find a second equation. And in the second equation, I'm going to have VI and I'm going to have VF, right? If I make VF2 the subject of the formula here, in the second equation, wherever I have VF, I will substitute it with something that has a VI in it, and therefore we'll be able to solve for VI immediately. You will see when we get to that. Okay, so you could make VI2 the subject of the formula. It doesn't really matter. You'll just take longer to solve it. Okay, it doesn't really matter. Which one you make subject of the formula, you get to the same answer in the end. So I'm choosing to make VF2 the subject of the formula. That is equal to, so this 0,2 is going to go to the other side and it's going to change its sign. So I'm going to end up with VI2, 2 minus 0,2 is 1,8. Okay, so this is one equation that I have. Remember, I need two equations in order to solve this. I need two equations because I have two unknowns. Now, where am I going to find the second equation? Because I've already used up my equation for conservation of momentum. Where am I going to find my other equation? Let's go back to the question. The question says two balls with the same mass collide elastically. That's the keyword, elastically. This is an elastic collision. What does elastic mean? Elastic, we covered this in a previous video. Elastic simply means that the kinetic energy in the system, the kinetic energy does not change. The kinetic energy is conserved. It doesn't change. So the kinetic energy of the balls that we started off with is the same as the kinetic energy of the balls that we end up with. Okay, so the kinetic energy that I have up here is the same as the kinetic energy that I end up with after the collision down here. Okay, so how do we express that mathematically? How do we express that in the form of an equation? Let us do that. Kinetic energy, EK initial, just like we did for momentum, right? In this case, I'm going to say EK initial is equal to EK after. Okay, is equal to EK after. Right, the kinetic energy does not change. And what is the equation for kinetic energy? Well, the equation for kinetic energy, we know that EK is equal to half mass of the object times the velocity at which the object is traveling. This is our equation for kinetic energy. So we're going to have to apply this equation for both the balls in both the system before the collision and the system after the collision, and we're going to have to equate the kinetic energies. So I'm going to start off with ball number 1. Actually, before I actually do that, I'm just going to express this thing nicely, and let's just say kinetic energy of ball 1 plus the kinetic energy of ball 2 is equal to, let's say, initial, right? Initial kinetic energy of ball 1 plus the initial kinetic energy of ball 2 are equal to EK, final kinetic energy of ball 1 plus the final kinetic energy of ball 2. Okay, that's all that it is. See, this is exactly the way we did it for conservation of momentum. But in this case, because our collision is elastic, this is conservation of energy. The energy does not change, it is conserved. So we keep the energy the same for before the collision and after the collision. Right, so now we just, for each one of these terms, we substitute half mv squared for each one of them, right? Because that's the total. So for ball number 1, we've got half. We've got m for ball number 1. We've got vi, initial velocity for ball number 1, squared, like that. Okay, then for ball number 2, we've got half. The mass of ball number 2 is just m. Then we've got the initial velocity for ball number 2 squared. Okay, so that is that there. Then all of that is equal to half m, that's for ball number 1, the final velocity for ball number 1, f for final velocity for ball number 1 squared, do not forget the squared, right? Do not forget the squared, plus half m for ball number 2, final velocity for ball number 2 squared. Okay, now you can see that if I divide everything, same logic as for the previous equation, I have an m there, I have an m there, I have an m there, I have an m there. So if I have an m for every term, if all the terms in the equation have an m, then I can divide everything by m and just cancel the m's out, so that I don't have to worry about m, right? I don't have to worry about that m there. I don't have to come up with a third equation. So that m and that m will cancel, that m and that m will cancel, that m and that m will cancel, that m and that m will cancel. Okay, then what am I left with? Well, what I'm left with is, I'm left with 1 over 2 velocity initial of ball number 1 squared, plus half velocity initial of ball number 2 squared. All of that is equal to half velocity final of ball number 1 squared, plus, I'm going to write it down here, half velocity final of ball number 2 squared. Okay, and now I just have v1 and I have just my velocities. Okay, now I can substitute the values, the actual values that I have. We know that the initial velocity of ball number 1, if I can go up to the question, the initial velocity of ball number 1 is 2 meters per second, and the final velocity of ball number 1 is 0.2 meters per second. And the initial and final velocities of ball number 2 I don't have. Okay, so that's the information that I have. So now I can just substitute 1 over 2, vi is 2, vi1 squared is 2, so that's going to be 2 squared plus 1 over 2. I can actually cancel all the halves again. Let me just, before I do that, just to make this equation simpler and easier to work with, remember this by the same logic that I used with the m. Remember what I said with the m's, right? I said with the m's that I've got m everywhere. So I'm just going to cancel the m's out. I can do the same thing with the 1 over 2. Okay, so let me show you. I've got a 1 over 2 there, I've got a 1 over 2 there, I've got a 1 over 2 there, I've got a 1 over 2 there. So if I divide everything by 1 over 2, the 1 over 2's will just cancel out. So I'm just going to cancel them out. All of them, I'm going to cancel them out. The same as I did with the m, right? Exact same thing as I did with the m. So now what I actually have is just this. I just did this so that the equation is easier to work with. If you don't want to do this, you can avoid doing it. It's fine. It's just mathematical. It makes more sense to do it. So vi1 squared plus vi2 squared is equal to vf1 squared plus vf2 squared. Okay, so that's what, look at how much more simple this equation looks. Okay, now I can actually start substituting. So I know that the initial velocity for ball number 1 was 2, it was given in the question. And I know that this one I don't have, vi2 I don't have squared. vi2 I don't have. vf2 I've got from the question, that's 0.2 squared plus vf2 squared I don't have. Okay, so now I've got my second equation. Let me just simplify it. So what I'm going to do now is I'm going to say I've got 4 plus vi2 squared is equal to 0.04 squared. I'm not squared. 0.04 plus vf2 squared. Okay, so now what I have is this simpler equation. I can simplify it further, but this is my second equation. Okay, this is my second equation. My second equation has VF and VI in it. Remember what my first equation was. My first equation was this one here. It has VF and VI in it. VF2 and VI2 in it. VF2 and VI2. What does this one have? It has VI2 and VF2. So we've got two unknowns and two equations. And now we can actually solve we can solve for what we are looking for here. Okay, so let us go on ahead and do that. So we will substitute. We know that if we go back to our first equation, our first equation is VF2. VF2 is equal to that, right? So wherever we see VF2, we're just going to substitute VI2 minus 1,8. Okay, wherever we see VF2, we're just going to substitute VI2 minus 1,8. Okay, that's exactly what I meant when I said I'm going to make VF2 the subject of the formula so that we can remove VF2 in our second equation. Now we're actually going to remove VF2 in our second equation. Wherever we see VF2, we're going to substitute VI2 minus 1,8. So there's VF2 there. So we're going to substitute it there. So when we put in our parameters there, that's 4 plus VI2, we don't have this is actually what we've been asked to solve in the question, plus 0,04 plus open bracket VI2 minus 1 minus, let me just write it down because let me try to squeeze them. I'm just going to take that 4 to the other side, okay? I'm going to take that 4 to the other side, and I'm going to put a negative onto that 4, and I am going to simplify that. So what I'm going to get is 4 minus 0,04 is going to give me 3,96. Then I'm going to have plus V. Now it's just mathematics. The physics part is done. Now it's just mathematics. Okay, that is equal to VF2 squared. Please do not forget the squared. Please do not forget the squared. Okay, so we've got 3,96 plus VI2 squared. Don't forget the squared. Wherever we have VF2, remember we're going to say VI2 because we've got VF2 there. We're going to put it VI2 minus 1,8. All of that is going to be squared. Okay, and then we are going to, now you can see that we've got just VI2s in there. So now we can actually solve for VI2. Okay, let's solve for VI2. So what's going to happen is that we're going to have 3,96 plus VI2 squared is equal to VI2 squared minus 3.6 VI. Now I'm just using the FOIL method to multiply out the brackets, right? Just multiply out the brackets. Then what is 1.8 squared? Let's use our calculator there. 1.8 times 1.8, that's 3.24. Okay, so that's going to be plus 3.24. Okay, so this is me just extending this bracket, okay, multiplying it out. Okay, so I'm just using the FOIL method there, and then what we have now is we can see that this VI2 squared here and that VI2 squared there will cancel each other out, right? If this one goes to that side, it becomes a negative, and then I have a plus VI2 squared minus VI2 squared, then they cancel each other out. So that and that, they cancel each other out. Then what we are left with is the following. We've got 3,96 is equal to, I'm actually going to take that to the other side, right? So I'm just going to say 3,96 plus 3,96 comma 6 vi2, then plus, or minus rather, minus 3,24 is equal to 0. Actually, wasn't supposed to bring everything to one side, but it's just mathematics, okay? Let's just solve. So what is 3,96 minus 3,24? Let's see. 3,96 minus 3,24 is 0,72. So that is 3,6 vi2 what did I just get? Plus 0,72 is equal to 0. Okay, and when we continue to solve this, what happens is that we've got 3,6 vi2 is equal to 0,72. Okay, then we divide both sides by 3,6, divide both sides by 3,6, then what we get is vi2, which is what we've been looking for. Vi2 is equal to 0,72 divided by 3,6. What is 0,72 divided by 3,6? That's 0,2. Here we get 0,2. We actually get minus, right? Because the 0,72 went to the other side, changed its sign, so that's 0 minus 0,2. Okay, so we've got a negative 0,2 there. Hi guys, Goma here. In this video, I made a mistake. I made a mathematical mistake that affected my answer. It's a small mistake that I made, and it had an impact on the answer. In this case, the impact wasn't that much, but a mistake like this could cost you dearly. So I hope when I was making the mistake, all of you were screaming out, comma, comma, that's a mistake. Okay, so the mistake that I made, so the principle, the approach that I used is okay, but the mistake that I made is right here, right? So here, this is actually supposed to be a plus. Okay, this is actually supposed to be a plus. You see, it's a plus there. Why? Because I took the 2 to the other side, so it's going to be 2 I took the 0,2 to the other side, so it's going to be 2 minus 0,2, and 2 minus 0,8 is positive 1,8. Okay, so that sign there has to be a positive instead of a negative. Okay, and I used this further down to substitute in the equation, and I got see, I used a negative there instead of a positive. It's supposed to be a positive, and therefore that is going to be a positive as well. And then that is going to be a negative. Okay, so this is going to be a negative, then it will be a negative here, then what I'm going to have is a negative here, negative there, negative there. Okay, then my answer here was actually going to be positive. So it turns out, in fact, that the answer that we assumed, the direction that we assumed for ball number 2 was actually correct, contrary to what I said in the video. Okay, the initially assumed direction was correct. And don't forget your units. Okay, if this was me writing this exam, I was going to lose a bunch of marks. See, meters per second. Never forget your unit, never forget your direction. Just either put in the plus there or put in the direction east. Okay, either one is fine. Okay, so that was a mistake that I made. It had a little bit of it. I'm lucky it didn't change the numbers. It just changed signs. Okay, but still be very careful of such mistakes. Don't make them. That was a naughty mistake from me. Okay, I will see you guys in the next video. Number one, lesson number one. Lesson number one, lesson number one.